take the opportunity to actually, basically, I remembered what I wanted to show you before. Now, based on Andreas' great talk, and it's some more things that we can see in the tools menu that might be important or interesting. So essentially, you can use Lead-DBS also to export PDF files, similar to what the pipeline does, also with a 3D viewer. But it needs some configuration, and you need LaTeX and so on. So I guess you need LaTeX in your server as well to do that. But what is much easier to export the datasets is actually PLI files, which have an open, they're basically an open format of 3D files, and it's pretty quick. So if we say we export PLI files for this selected patient, it's the same patient we process together, then it will in the background export the results as like an open format that you can then open in nearly any 3D viewer. And I can show you, I just did that. So again, it was under Tools, and then Export, and then PLI. And it creates an export folder with PLI, and we'll have the anatomy here. And you can maybe open that in a 3D viewer like Surface or so. And let me see, is it already done? It's still doing things. So still exporting this combined scene, PLI. But once it's done, you can open that in, something like Surface or whatever different software, right? So this is also a way to share the results with people. It's maybe not as convenient as a PDF for clinicians, but you could use it in 3D slicer or whatsoever. And in Berlin, we also we created a web server where we can now, where our clinicians can now look at these results from the intranet, right? So they can, for programming, they have a database, and they have these 3D reconstructions that you can see in the web browser. Might even be that you can directly open these in Chrome. I wouldn't be surprised. No, you can't. Okay, but there are viewers on the web where you can open these. And another option is to export a zip file for, in this case, STN. And what it would do is it would create the PLI, as we have just seen, but it would also create screenshots, automated screenshots with the standard views, and then you would have, some images and some report. So it's a bit similar to maybe a PDF, but not for clinicians, really, right? And if you're interested in the PDF export, also you may maybe let Nick know. We haven't done this much in the past, but it should work if you configure everything correctly. And now you can see, so it has, since I exported this zip file, it has created the PLI files again, but it will also now take screenshots. So you see in these views, it will have files that like just image files that from the left side, from the right side, and from anterior, posterior, and you could share these zip files or upload them to a web server also. If you like Slicer, just out of curiosity, that Slicer will also work on these PLI files. So we have to switch to the 3D view, but here we can see, now I just imported the electrodes, but if I do combine scene, I think it should show us all the scenes, and you could maybe even use spectrography or similar things in Slicer, basically. Now it created a zip file, and inside of that we would have the combined electrodes and these views, right, where we have good orientation of what is what. Okay. But now let's move to normative connectomes, and I think that's a topic for some of you that you're really interested in, at least I heard so. So the idea before LinkedIn, I showed you how to process diffusion MRI and fMRI from your patients, but you might have large databases without their specific connectivity information, and you cannot acquire them after the electrodes are inserted. So what we've done in the past, and I've shown you in the talk, is to use normative data, right? Again, the connectome is the parts of the brain and the connections. I've shown you that. And in 2005, Olaf Sporns and Patrick Hartmann both introduced these topics. And so I think Olaf Sporns said the human connectome, and Patrick Hartmann used the term connectomics. And so there's one quote from Olaf Sporns' second book, and he said, "When I googled the term connectome, just to be sure no one else had thought of it earlier, I remember getting around 10 hits, none of them relevant to the brain. As of April 2012, the same Google search returns nearly 250,000 hits. What happened?" Right? So you can see just this name and just this concept had a tremendous impact on the field. And we have been analyzing brain connectivity decades before them, right? So it's an old concept to look at connections in the brain, but the idea to try to model the whole brain actually did have quite some impact. Here's just some impact on the German big newspapers. So this is not really global, but you've seen surely such images also in your newspapers. Then there's Sebastian Seung from MIT, who even says, "I am my connectome." It's maybe taking it one step further, and he would say that there's one self that changes rapidly from moment to moment, becoming angry and then cheering up, thinking about the meaning of life, and then the household chores. And the other self is much more stable, retains memories from childhood over an entire lifetime. Its nature, what we think of as personality, is largely constant. And he basically claims that this part of self is the structural connectome, only changes very slowly over time, but this one may be the functional connectome. It's what your brain is currently doing and what is happening in terms of connections. And he would say that your self is basically based on your connectome. But of course with imaging we only have a very low resolution, so we cannot really see everything. Then the impact of the term connectome, as I mentioned, there are certain initiatives. So the Open Worm project is more about the worm connectome, but then there was the Blue Brain project in Switzerland, and the Human Connectome project, everybody knows that, big initiative in the US. And then Europe answered with the Human Brain project, and then there was a 1 billion, that was 1 billion euro, and then Obama wants to map the human brain with the 3 billion 10-year research project. So you see there's also some competition, and now we have the Chinese brain project actually happening, I think, as most of the time here in Shanghai with new scanners and everything. So all the world is really trying to mine the connectome, and there's an Open Connectome project for the Linux fans. Barack Obama said these words, and I think they apply perfectly for this workshop, because he said we can't afford to miss these opportunities while the rest of the world races ahead. We have to seize them. I don't want the next job creating discoveries to happen in China or India or Germany. I want them to happen right here in the US. Right? But we are Germans or Chinese and Germans, and we also want them to happen in our countries, I think. Or at least we want them to happen. That's much more important. And but it shows that, you know, with the Brain Initiative, politicians see a great potential in connectomics. And now the idea, again, is to have connectivity between all areas of the brain. And with that, you get a wiring diagram of the brain, right? You get regions and you get their connections. And the question now is, what is all areas of the brain? All areas of the brain is a very loose concept, but you can define them on a macro scale, a mesoscale, and a micro scale. And everything that we do with imaging is unfortunately on the macro scale. So always have these large brain regions like here, and we parcellate the brain, and then we want connectivity between these parcels. And we have shown you this before. We have quite a few of these parcellation schemes, and this is from the new paper where we also have all the citations based on the parcellation. So you can see some of them are really whole brain; they cover everything, and then some have more focus on only the cortex, and some have specific subregions. Like, I don't know, these are really motor area templates and so on. Structural connectome is based on the white matter connectivity, and unfortunately only tool that we can use for that is diffusion MRI, and as I told you before, it's a bad method. Then the functional connectome, so this is just one normative connectome that we've made. We've talked about that. And we also validated this normative connectome based on big tracts and so on, and thalamus parcellations and so on. So these were the first efforts we made to create a normative connectome in the brain. And then there's functional connectivity, and this is the, I would say, Nobel Prize figure of Bharat Biswal, or it's not Nobel Prize, but it's really important figure where it was first shown that the two motor cortices are correlated in the resting state. So you just put a person in the scanner and you get a correlation between homolog areas of the brain. And functional connectome is based on often resting state fMRI, and it's also a terrible method. It's also the only one we have, really. So we have two terrible methods, and these are the only ones we can really use without cutting the brain open. But we really should bear in mind that they are not good methods, even if you have a very great processing pipeline. So this is just a video which shows the bold fluctuations, so the centrality fluctuations in the sliding window analysis. So you see that this changes over time. So it's a bit like Sebastian Sohn meant that this may really change based on the state of your brain, whereas the diffusion MRI connectome is slower and usually only changes over years or months, if at all. And how can we formally store and characterize such connectomes? Well, we take T1s, then we can normalize them, we build a group template, and then we have the diffusion data and the resting state data, and we can then, for each parcel of the brain, we can create these connectivity matrices, which can be based on different metrics. But this is basically how we can store such normative connectomes. Another way is, and this is then graph theory. You can analyze these matrices and make certain statistical properties of these. I won't go into detail on that, but if you're interested, I think all the literature by Olaf Spons, but also this Rubinov paper about graph theory is pretty influential. Also the books by Olaf Spons are excellent to start with graph theory. This is again the clustering and so on. And then nicely for us, a development that also came up with connectomics was open datasets. So it's actually a pretty new phenomenon, but people start really putting brains on the internet, or have started. I think the very first really big initiative in the imaging world was 1,000 functional connectomes. And it was just 1,000 resting state fMRI datasets, where a lot of people in the world just put their resting state data together. So every part of that dataset has different properties, was scanned on a different scanner, has different TRs and so on. It's terrible to analyze it. I've done it once when I was still a bit younger, and because you have to account for all of these different scanners and resolutions and so on. Then people started to have these really enhanced connectomes where one side specialized on just acquiring 1,000 brains, and or the Human Connectome Project, of course. All of them were scanned on the same scanner, and you have really a homogeneous data set. And then also people started to scan disease-specific data sets. For us, I think the PPMI is the most important one, because that's really for Parkinson's, but there's a lot more. There's ADNI for autism, and then ABIDE, I think, for I'm not sure, but I know that corporates for schizophrenia, so there are a lot of these online that you can find. Actually, Google recently added a dataset research tool where you can look for datasets on Google. And we have now started to aggregate these normative connectomes in a pre-processed and easy-to-use way over the years. Actually, we started, I think, in this publication 2014, where we had our own data, 20 subjects that we scanned our own. It was a different time. We would never do this again, because you have so many resting state scans on the internet. Why should you scan a single more patient, right? Because but what we did at that time, it was different, and we had 20 healthy controls. They were processed with the Gibbs tracker, and we have only structural data. The second then was this 170 subjects, which were based on a publication population, and then we had we used the human connectome project data. It's only 30 subjects, but it's really great data because it was acquired on specialized MRI hardware, and it's 30 controls published here, and then our pre-processed version here. And then we have PPMI, it's actually a mistake here, PPMI dataset, 90 PD patients, and we have functional data from these PPMI patients as well. And then for normative, for the fMRI, we have healthy subjects and 1,000 controls. Right, so you can see all of these datasets are more or less in a format that is ready to use using Lead-Mapper, so our tools. So you can take any Nifty file as a seed and run connectivity based on these datasets, right? And still they are pretty inhomogeneous, right? So sometimes it's 1,000, sometimes it's only 20, and sometimes it's Parkinson's and so on. So we did these as we needed them. As you can see, but still I think they can be useful. And that is everything for this talk. And now I would want to start using it. And what I want to do is open the same subject as we have done before. And first of all, we have to create a stimulation, or we still have one. Yeah. So we have a stimulation in our folder. And again, we have the Nifty files of the VTA and write. Now, if we open this file in Lead Connectome Mapper, that's the patient, that's a different tool altogether. And Lead Connectome Mapper is more about normative data. Now, here you can see the patient is loaded up here. And we can say we want to use the stimulation that we created, right? That's the name we gave the stimulation. And then we want to create a functional connectivity map based on a normative connectome I have installed here. And currently I don't have any structural connectome in here, so we will just do functional MRI. And we say we want to use from this PPMI dataset only the patients, right? And then we can say what do we want to do from it, and the most basic thing is to do connectivity map from the seed. And if we do that, what Lead Connectome Mapper will now do is to use the VTAs in MNI space and use the normative connectome, only the patient data, and will create us a map, a connectivity map from these seeds. Right? It's actually as easy as that, and that doesn't work.
Andy, I got lost. So
you get lost? Okay.
You are using your own patient data at which point there? What is the use of your patient data?
The VTA.
Just the volume.
Yeah. Yeah. And apparently it didn't work, so there seems to be a bug. Sorry about that. Okay, I think, so unfortunately I think the problem is actually just because I open lead mapper from within Lead-DBS, and there seems a bug for that. But if we say, if we open it again, just enter lead mapper, and now we say we want to use the VTAs, and we want to do that. Now it should work. Yes, looks better. So sorry about that. Currently you have to start lead mapper from scratch. But what we do is we load the patient here, and we use the VTAs, but we don't use the connectivity from this patient, but we use different patients' surrogate.
So you were trying to do it with patient-specific parameters.
Yes.
That's okay, or you want?
Yes, of course. Yeah. Yeah. With patient-specific parameters also should work, but it will of course will add noise, right? So it's a trade-off between, of course, you have the patient-specific tracks, but that's true. So you can, if you have patient-specific fiber tracks here, you should be able to see it in the drop-down, and then you could choose patient-specific fiber tracks, and you could also get a map. Let's see how fast it is. Okay, it's 30%. In the meantime, I will open a different MATLAB and show you some more thoughts about this. Because, so what we're currently doing is we use the VTAs as seeds. So we want to know what is this VTA connected to in a normal brain or in a Parkinsonian brain. But we can also use any other nifty file to do so, right? So we can, instead of using the VTA or any patient, we can just use a nifty file, right? So actually this part where we choose the patient is optional, right? You don't even have to use a patient here. But you could just start with manually choosing a seed, manually choosing a nifty file, right? So if I would just say I choose a seed and ignore the first and say, you know, I just use the same, the right VTA of this patient, right? That would do a similar thing, but only to take the right VTA. So I ignore this completely, but I choose the seed, and then I say again, run connectivity now. That would work. The other thing that I could do is to choose more than one, right? I could just select the right one and the left one. Now I have two seeds selected, and I can do the same thing. Okay. Now I could also take anything else instead of a VTA. I could just say, I have a hand-drawn lesion of your tumor or whatever. I could just select that, right? And what's important here, I could also import a text file. So I could select, I could make a text file which points to certain nifty files, right? So, for example, if I have, let's say I have these three nifty files, I could save a text file that specifies the path to each of these nifty files. And I say, okay, this is the seed list .text, and that's on my desktop now. It's here. And I could now, in the second one that I don't use currently, I could say I choose not a nifty file but a text file, and I choose that. And now it would also include 3 regions of interest. Did everybody understand that? It's not complicated, but we can either select multiple nifty files or we can select a text file. Now, sometimes we're not really interested in VTA's connectivity, but maybe we want to know just connectivity between, or let's say we want to know connectivity between VTAs, but also the SMA, right? And we don't want to map, but we want connectivity strength between these. Right? What we can then do is to select an SMA ROI and 2 VTA ROIs, and then we would know the connectivity between them. And to do so, we then have to say connectivity matrix here. Right? So connectivity matrix instead of connectivity map from seed will just give us a seed by seed matrix of how strongly are these connected. So what you could do, just as an idea, is you take an SMA seed and you take 20 patients, VTAs, and then you calculate the matrix and you get a 21 by 21 matrix, and then you can use only the entries between the VTAs to the SMA and correlate that with UPS and right? So that's one other, I think, popular choice, and you can do, of course, the same for fMRI, but also for structural fMRI.
And how variable is the connectivity strength
A variable?
in individual subjects compared to the normative data? Is that informative?
You mean
So if I take
VTA
that,
to SMA?
I do that, say, between SDN and SMA
and
for an individual patient, how variable that is from patient to patient compared to the normative data? It doesn't provide any information.
I think it's pretty variable, and it's so variable even if you scan the same patient twice. So that's the problem with the patient-specific data in fMRI, especially that if you scan the patient twice or 3 times, it varies a lot. It often varies more than the UPDS score will. So, but I'd say that the strength of the normative connectomes is that you use an atlas that is more or less robust and doesn't change, and the only parameter that you change is the VTA placement. And of course, the downside is that it doesn't reflect anything about the patient-specific connectivity.
And the connectivity strength would not be very informative in that context.
I would think so, because it would inform you of what that region would be on average connected in your brain. But it's a different type of information, of course. It's a bit like whether you look if it's in the Atlas SDN or not. So there is a limitation, and you have to assume that your patient is similar to the average connectivity, but then you don't have the noise problem. Okay, but so 2 things basically: connectivity map from seed or connectivity matrix. The rest is more or less not so important, but you could also have what's called exclusive connectivity map from seed. Would be if you have 3 seeds, then it would use the partial connectivity, partial correlations in fMRI, but use a slightly different thing in diffusion MRI. So that's why we don't call it, we call it exclusive connectivity. So it's what this region is connected to, accounting for the other 2. It's not so important, I think. And the same for exclusive connectivity matrix. That would be basically the inverse of the connectivity matrix. So the partial correlation in fMRI and in diffusion MRI is a bit more correct. Right, but I think these 2, yes?
Sorry, if we run it from connectivity visualization, is the same?
From
connectivity visualization from the render?
It doesn't give you the maps, no, it's not the same. So it's a different output actually.
So we should do that after if we want to.
Yeah, it depends. I think the visualization is really just about visualization. That's why I think I told you yesterday we don't really use it that much. But this is basically to do stats and so on. So now maybe we can have a look at this one. It's done now, right? So now we have inside of that stimulations folder, right? So we are now in the patient stimulations and the stimulation name. We have a new folder which is called PPMI, so it's called after the connectome. And we have a certain amount of files, and I would say the most important one is this one, but they are all pretty similar. And that is the connectivity map, so it's seeded functional connectivity across 90 PPMI patients or 74 PPMI patients from here, and gives you estimates of how much functional connectivity you have to other brain regions. And you could use that file, for example, in the great software Surface that we use a lot. And you can basically visualize it and say, let's say we want to show connectivity, functional connectivity like this, and then anti-correlations like this. So you see anti-correlations to motor cortex and then maybe positive correlations to these regions. So this is a way of getting an estimate of how your VTAs are on average connected in a Parkinsonian average brain.
And when we are talking about tracks, as you were saying today, that to get the connectivity profile, we should look with EO-RMAP or something like that.
No, tracks would be actually, I just don't have a connectome here, but you can just say include structural and you select connectome and then you get a different file.
And be able to visualize it like that?
Yes, but it's really different data, right? So it looks like streamlines in the Nifty, so it would be much more noisy in surface. But
today you were showing the fiber track formation from electrode to electrode and changing it.
Yeah, no, that was in the visualization mode. Yeah. So it's a bit different. So Lead-Mapper always gives you Nifty files, not streamlines. So you can use them in software like SPM or so to do stats, but if you want to show tracks, then the visualization mode is better. Yeah.
How to show it?
To show what?
To show the
Any Nifty viewer.
yeah, but it's only in the file, so I need to synchronize with the program. It's very results.
Sorry. Yeah. Yeah. That's what you get. It's in M&I space, right? So yeah, this will all be always in M&I space. Okay, so and I think you were asking about how to then create these R maps, right? That there is code for that. It's called EA R map, and you would enter the, let me see, like this, the files, the regressor. So it would be like, files would be a cell array pointing to your Nifty files. So maybe something like the path to your Nifty file. And maybe some more of these, right? So you would add as many subjects as you have to that, and then the regressor would be something like the clinical improvement. So it could be maybe 0.8 in the first patient and 0.6 in the second patient, and then the output name is just my RMap.nifty. And the mask, you can just for now say EA get mask, which will use a standard mask, and you don't supply this, and you say maybe correlation you want to use Pearson correlation. Then that will create such a map, and it's probably okay. I have to escape these. So it's probably, the problem is probably that we have supplied the same image 2 times, but let's try if we do 3 times, then it could work. Probably need a number of, a reasonable number. seems to. So usually this works pretty well. But usually we have at least 20 patients or so. Probably this just needs to be. Yeah. Now it works. Right. So now, and I can send you this text file if you want. And we have now created a fake RMAP that doesn't work because it's always the same image and we have different values, so all correlations I think will be 0. But yeah, that would do that. Okay, so I guess key thought here is a few things. So first of all, Lead Mapper is a tool more or less mainly for normative connectomics, but you can also use patient-specific data if you have it. And it gives you nifty files. You can then use these with any other tool you have, like SPM or FSL or so. And you also note that we have connectomics in different places in Lead-DBS, right? So we have it in Mapper, we also have it in Lead Connectome, which is more about patient-specific connectivity. We have it in the visualization mode as you've seen, and we've partly shown or bit shown. And then we even have it on a fourth instance, which is Lead Group. And any of these tools can help to answer specific questions, but there's no Connectome button that can be used for everything, because you really have to question yourself, what is my specific question, what do I want to show? And if you can, if you need help and you can formulate such a question well, then we can tell you use that tool for it. But it's sometimes people approach us and say, I have this data set and I want to do connectomics with it, and then we say, okay, there's so many things that you do, but you need a good hypothesis first, and then we might be able to help with a tool for it or not. Okay. That was that. Any questions? Do you think you've understood the concept, or do you want to try yourself more? And important is that you can install these connectomes here, right? So most of them are just downloadable from the website. And as you can see, in my case, I just have this one installed currently, so the rest is lacking.